Okay, over to you, co-founder, please. So I've started the recording section. Over to Miss Kenny.
Hello, everyone. Good morning.
Good morning.
Welcome to the second section of the AREFOR training. I hope we had a good section last week. So, my name is Akindele Oluwadamilola Kehinde, and I'll be introducing our speaker for today. But before then, last week, John Bagilico started with the linear regression. So Mr. Martin Bagaram will also be continuing from that part today. So briefly, I will be reading the citation of Mr. Martins. Okay. Yeah. Mr. Martin is an experienced optimization specialist with a demonstrated history of working in the higher education industry. He's skilled in Java and Python. He possesses advanced knowledge of SQL and machine learning. Mr. Martin obtained his master's degree in industrial engineering and bachelor's degree in informatics from Morocco. He's a strong research professional with a Doctor of Philosophy training. Wow. Focused in data science and optimization from the University of Washington. So, permit me to welcome Mr. Martins.
Thank you, Kelly, for that lovely introduction. And I think I can take it from here.
Oh, yes, sir. You can.
So I will share my screen. And I think she said everything you have to know about me, except what? Except everything you have to know about me. So basically, I have been in school for a long time, very, very long time. And I accumulated I have accumulated 4 master's degrees. And,
wow.
Yeah. And I am completing a PhD very soon, hopefully. And basically that's it. And currently I'm working for Amazon as an applied scientist. And what an applied scientist does basically is a data scientist with software engineering skills. So you combine both and then you are called applied scientist. So you write codes and you test it and then you push it to production where it can be used by many engineers. And if someone has been on Amazon.com, you can see that at each second it is millions of transactions that are going on. So you need some kind of mathematical knowledge to be able to model all that aspect. And then you need to have some computer software or computer engineering skills to be able to implement it. So why an applied scientist? To explain that job title, because it is quite vague, is that they realize that the software engineers know software engineering, but they don't know the modeling and the mathematical aspect behind the things. So that wasn't sufficient. So you have a data scientist that can analyze the data, and then they cannot put it into production. Or you have a software engineer who knows how to write a software, but they don't really know what the data is telling them. So they needed someone who can do both. And someone who can do both is what they call applied scientists. It pays quite well. That's what you need to know. Maybe it pays better than being a software engineer or being a data scientist. But the downside of it comes with you need to be quite skilled and you need to learn the best of the two worlds. You don't need to be the best, but you need to be good at least. And the other thing I will talk about before continuing my presentation is it doesn't really matter what you study, because I started my journey with a bachelor in forestry and then a master in the French system, they call it an engineering degree, but it is equivalent to master. In the forestry, but applied to geomatics. And I realized there is one geomatician here. And later I did a master degree in Portugal. That was a kind of forestry, but it was decision support systems. And then I ended up doing another master in remote sensing in Italy. And then when I came to University of Washington, while doing my PhD, I did a master in industrial engineering. So I was carrying two hats at the same time. So basically that's it. I have been always looking for knowledge, and wherever there is something new, I am there trying to learn it and trying to improve it. And what I have learned all along is what really makes the difference between someone who is good and someone who is great is just some small things, like details. Like, so someone who is great knows about small details that can make a big life change and make big life change decisions. Someone who is good just know how to click some buttons. So this presentation, I didn't take it to a very high level. I still kept it very basic. And then we try to go into those basics. And if you have more advanced questions, I will be happy to answer them, but I didn't include them here. Like I told you, I realized how the background was diverse, and I just wanted to know that if you have the basics, you can go far, far away. Because all this material, you can find it online. What makes the difference is how deep do you understand them? And after that long introduction, let's go to the main topic. So the regression, that's what I am asked to talk about. But I couldn't talk about regression without talking a little bit about correlation. So what do we know? What do we call correlation? So what makes really the difference between correlation and regression? Because both of them are basically the same. You are trying to see the relationship between two variables, at least when it comes to linear regression. And the answer is a correlation is just trying to measure how things co-vary. If one goes up, maybe the other one goes down, or both of them go up, something like that. When it comes to regression, you are trying to predict one using the other. So this is one of the classic examples that you will find in R books, and it is the data set that is in R. It is known as iris data set. So if you want to answer to the correlation question, then the question you ask is, are the petals get wider when they get longer? So these are petals, right? So are they longer when they get wider, or are they wider when they get longer? And when you plot them, you can see that these are three different species. You see that it tends to be like, yes, when they get longer, they get wider. That's the idea of a correlation. And if we wanted a regression, then we would be asking a question differently, right? Can we predict one using the other? Then we go to regression. That's the only difference. And I think this can be useful when it comes to research. These are the details that I was talking of that can make a big difference. I mean, most software already implemented this correlation coefficient, but for some reasons, you will need some day to implement it yourself. And when it comes to implement it yourself, you need to understand what is happening to be able to change some parameters, because that's what makes a big difference. If you understand how something works, then you can change and tweak a few of it and make it better. So in general, X bar is the average of the first parameter, and Y bar is the average of the second parameter, and the S are the standard deviations. And this is supposed known, so I don't explain what is standard deviations. And correlation coefficient range between -1 and 1. That's the beauty of a correlation, right? Because it is normalized so that we know that it goes between -1 and 1. Because we have other factors like coefficient of variation and things like that, or covariance that are not standardized. So we need this to be standardized. And we know that when we have positive positive means positive correlation and negative means negative correlation. If you have questions, ask them in the chat room and I will get back to it while presenting. I don't mind that. Because I suppose these things are known, but I may be wrong. So last time when we were talking with John, I saw he presented that in general, you want your correlation to be bigger, like greater than 0.7. And my point is that that's true, but it's not always the case, because you can have a very big correlation of 0.7 and it is not significant. So what really matters is this correlation significant? And if you want to do it by hand, this is the formula you use, and R is our correlation coefficient that we calculated in this formula, this one. And the degree of freedom is something that is very interesting in statistics, and it is quite confusing to many people. So basically, the rough explanation is the degree of freedom is how many variables you can change without really changing your statistic. So for example, in this case, because I have two variables, so I have two means. So it means that I can change n-2 of them without actually changing what this t is. In another way to explain it is, if I am given n-2 element, then I can determine the two others. They have to be fixed. They cannot be changed. Because if you fix the mean, then you can change everything, but the mean has to finally be equal to what it was before. So, and since we have two variables, so we have two means that are fixed. So that's the idea of a coefficient of variation. Degree of freedom. Now, let's go to linear regression. That is the most basic regression, right? So the linear regression, you can represent your data as ordered pairs, where X and Y, X is independent or explanatory variable. Personally, I prefer explanatory rather than independent, because technically, if I am dependent on you, then there is already that relationship. So dependent and independent can be subjective. So I prefer explanatory variable and the responsive variable. And I want to highlight this thing because I worked with some people that are PhD students that are having very hard time understanding why they cannot perform linear regression on some data set. Like they collect soil data and then they have weather data from another place and they wanted to do the correlation. And I am like, okay, where is your ordered pairs? Because you cannot just take soil data from, I don't know, Togo, and then go and collect some weather data in Nigeria, and you have now no relationship between the two, and you are trying to do a correlation between it. I'm not saying it is not doable, but this is already making a lot of assumptions before starting making such a comparison. But the easiest example that we can come up with is the weight and the height. If you want to predict the height using the weight, then you need to measure it on the same individuals. So I don't know, I cannot just take the participant here and measure the weight on half and then measure the height on the other half and to do the regression. I need to measure them on the same individuals. So the idea of regression is we want to go beyond the idea of are they related or not and try to use one to predict the other. And regression analysis basically is this. And this is something that I wrote here on purpose. This is a y hat. Y hat as an estimation of what is the value of y. Okay, if we take this plot, you have miles per gallon, that is the y-axis, and then you have on x-axis what is known as a vehicle weight. So we are trying to see the consumption of vehicle based on the weight of the vehicle. So the idea is heavy cars consume less in this, consume more in this case, fuel. And Y hat is the estimated miles per gallon. And it is not Y, because if we put Y, then we need to add here plus some error. Error term as something that we don't know, like residuals. I pause here and ask, is there any question, or this is so basic?
Well, so far nobody raised hand or wrote anything in the chat.
Okay. Now I feel like I underestimated you guys. So if we go to our regression, that's what the software does. And like that's what I was talking about, what makes a difference between someone who is great and someone who is good. So in this question is we have Y given to us by the data we collected. We have X that is given to us, and the A and B are the things we don't know. B is the slope of this line that we want to fit, and the A is the intercept with the Y-axis. So the question is, what is the value of A and what is the value of B? So basically what you do in the software is you try to calculate what is the standard deviation, that is S of the Y data set, and then what is the standard deviation of X, and this is small r. If you remember, this is our correlation coefficient. So that will give you B1. And then B0, you will just take the Y, the general Y. So this is the average of all the data set on Y. And then you take the average of X and the average of Y. And you already got the B1 from here. So that's it, you get the B0. Basically, that's all you have to do. That's all the software does. When you fit it when you give it to R, in the background, exactly this is what it does. There are other methods to estimate these parameters, but I am not going to cover them because they are considered like advanced material where you need to understand what is optimization and try to minimize the OLS, ordinary least square errors. And I don't want to bore some people who don't want to go along that line. So let's take the example of iris data set. We have the length and we have the width. And so if we calculate, this is the average width and this is the average length, and with their standard deviation. And this R, we can get it from correlation. And I showed at the beginning how to calculate it. You will get this slide if you want. So from there, if you just fill in the data, you get the slope and you get the B0, that is the intercept. And I want to pause here and ask you if you think this B0 makes sense. Who wants to speak? Okay, nobody. So do you think this B0 makes sense or not? This virtual learning is very difficult. You can't see the face. You have no idea who is doing what. Maybe my friends are right now. I am curious. Shri, do you mind answering?
So, Shri, can you hear us? I'm going to activate your microphone in case you forgot to do so.
Hello.
Yes.
Hey.
Where are you joining us from?
Nepal.
Nepal. Okay. Thank you for joining us. And sorry for picking on you, but I liked your name. So, so do you think this this B0 makes sense?
Sorry.
So do you think this B0 of minus 0.364, it makes sense to have a B0 like this?
I'm
Okay.
sorry, I don't know.
Okay, it is fine. There is no right or wrong answer. The whole purpose is I want to make sure you are engaged and you are following. So I want to give the answer here. Thank you for participating, Shuri. That's how you say your name, right?
Yeah,
Thank you for participating.
thank
So
you.
I want to give the actual answer, but I will give it later. So when you calculate your parameters, if as a data analyst or data scientist or whatever you call yourself or researcher, don't just present the values and go and take a coffee or go and talk with your neighbor in the corner. You need to question your data and ask, does it make sense? So in this case, what B0 is telling us is, it is somewhere here, it is not represented, that if the length of the petal is 0, then the width will be minus 0.36. That's the interpretation. So I leave it there, and you can see if it makes sense or not. So basically what it is telling us is, if you don't have any length at all, you will have a negative width. And that may not make sense. It may make sense. So you need to question your data all the time you will be analyzing data. Each single parameter you calculate, you need to question it. You need to see if it makes sense. If it doesn't make sense, that is what makes the big difference between a data analyst and a data scientist. A data scientist knows what the data is telling them, and if it makes sense in business. A data analyst just analyze the data and they are like, oh, this is not my problem. That's what the input was, and this is the output that goes along with. And I want you to understand it. So now we go to interpreting parameters. The first question that we may ask is the slope. The slope describes the estimated difference between y and x. And the question is, how good is this 0.41? And some people will say that it is good. And the explanation here is, if x, the length, changes by 1 unit, the width will change by 0.41 units. And this may make sense or may not make sense, but that's the interpretation we have here. And B0 describes the average outcome of y if x is equal to 0. And the linear model is valid all the way to x equal to 0. And that's what I go to say, which in many applications is not the case. So you need to be careful about B0. Sometimes it doesn't even make sense to have a B0. So now we can write the equation of this line, that is minus 0.36 plus this is x can give us the width is given by the length following this equation. And we have a coefficient of correlation of 0.96 and the coefficient of determination of 0.92. I will come back on this one, what we call coefficient of determination. The coefficient of determination is this ratio. What it says is explain the variation divided by the total variation. It is in the case, this one I need to stress is, this is in the case of linear regression. Only in the linear regression, what is in this slide makes sense. If it is multiple regression, forget everything that is on this slide. Except explain the variation divided by total variation. But same as taking the square of R, it is only valid if it is a linear regression. it ranges between 0 and 1. If it is multiple regression, that's not true. R squared tells you how well the model explains the data. So R squared of 0.8 means that 80% of the variation is explained by the line that you fit. So that can be good. That is considered good. And John last time said if you have over 0.7, it is good. But it is relative. You can still have 0.7 that is not good. We will go to those specific cases later. And deviation, so we can skip this because it is just explaining again how we go. So this is some kind of output from R, just an overview of what you will get as a result. And this is like a null variation, and it means when there is nothing, and the variation of the model. So basically the ratio will be this divided by that to get your R squared. And what they call intercept in R is what we know as B0, and the estimate was minus 0.36. And another thing that is overlooked by many people is what is known as a standard error. So in this case, we have a standard error of 0.03. And so it means that this estimate of minus 0.36 can go up by this value or can go down by this value. So in any case, it will still be negative. That's a very important information to have. Let's suppose that you have this, and then you have a standard error of 1.2. Then it means that this estimate is very uncertain. And those cases arise when you have a very low data set, like you have 3 points. You can fit a regression line just with 3 points. If you have like that, then your standard error will be high. It means that your estimates are very unreliable. And this is the p-value. I suppose we know what is p-value. Otherwise, the p-value is just the probability of observing such a value under the circumstances that this intercept was just 0. This, like there was no intercept. And this is the slope we measured before. So it will be under this, whatever your variable was, and the same. And then you have the p-value associated to it. And the very low p-values like this means that it is good variables. I mean, your model is good. And like I told you, if you divide this 6.3 by 80, you get sorry, if you divide 80.25 plus, this is unexplained, so you need to add it, 86.56. Okay, before we dive deeper, things to consider: when is it good to fit a linear regression? First of all, your data should look apparently linear. You cannot just, any data they give you, you just fit a linear regression. You need to look at your data and then decide if this data makes sense to be fit as a linear or not. And this is something that is quite confusing. And it was confusing to me, quite honestly, until maybe 3 years ago, when I had to write a paper. Then I needed to deeply understand what is going on. So many people will tell you that to fit your linear model, you need your data to be normal. But that's not exactly what it is. You need your residuals to be normal. That's the truth, not your data to be normal. Anyway, your data, you have X and you have Y. So which one of them should be normal? So both of them or one of them. But the truth is you should fit first your model and then you check the residuals if they are normal. And the mathematical explanation, I only got it last year. The truth is if you fit your model and the model is appropriate, then the model X is equal to A plus, I have to go back to this and to explain why it is like that. if you fit your model correctly, this model, then you will have residuals that I didn't write here. And this is a constant, so it can go away. This is just a constant multiplied by a variable. So if both of them works well, then this should be normal. And if these are normal, then it means this and this, they are the good models that fit the data, and it can explain why it is like that. It means that your Y will be normal as well. Does it make sense? I want you to understand that concept of residuals should be normal, not the data, residuals.
Mr. Bagaram.
Yeah.
Nobody asked a question about this, and I guess they would if they didn't understand, but there is one question about standard error, and I don't know if I should tell the person who asked it to ask directly.
I can see the question. Let me read it.
Great.
So I have seen in some research reports where scientists report standard deviation instead of standard error. When is one expected to report standard error? And when is one expected to report standard deviation? Good question. So I do research, so I will tell you what we do when it comes to research. So in reality, you should report the standard error, because standard error includes the standard deviation and the num n. So unfortunately, I don't have a touch screen. So the formula of standard error is the standard deviation divided by n, the number of observations. So what happens is if your standard deviation is quite high and your number of observations is high as well, then your standard error tends to be small. So as a scientist, personally, I do it, and many scientists do it. You tend to report the parameters that will make your argument stronger. So if the standard deviation, if you just want to show that, hey, look, the variability in the data is quite high, and you see there is no significant difference between this and this because they have very high variability, then you tend to report the standard deviation because it will give you huge values. And when you wanted to show that, okay, this, although maybe the difference between the two parameters or the two classes is not that big, the standard error will show that they are a bit different. So you tend to show standard error. But as a rule of thumb, if you present a standard error, you are always right, because you will use the information standard deviation has. The other way is you report standard deviation and the number of observation n. I hope I answered to your question. Someone asked, please, can the data for today's training be reposted? I'm just joining. Okay. Kenny, can you do that, please? And someone asked why the residuals have to be normal. I wish we were in a classroom where I could show you exactly what I mean. So, I will write what the actual model is, right? Y is equal to A plus B1.
Are we supposed to be seeing what you're writing?
I will send it.
Okay.
I wrote it in the comment. So the actual model that we write is X is equal to A plus BX plus epsilon. And what I'm claiming is that epsilon has to be normal distributed. And the idea of residuals being normal is, if residuals, why this needs to be normal? Because A is just a constant. So we can just even take A out of this equation. Because many people confuse and they think that it is the normal, the data that should be normal. So basically what they say is Y should be normal and X should be normal. But that's not necessary. It is not important to have it. Because B is just going to be, if you go back and you check how we calculated B, it is a constant. So we don't need it. if the model, this model that fits the data, x hat, y hat is given by a plus b bar x is a good model, then these residuals should be normal. Just the residuals. So we don't care really what the x, y is and what the x is. If the model is okay, the residuals should be normal. That's what you need to hold on. So basically what you do if you write some research or even if you work for yourself or for a company, what you have to do at the end is you check the residuals, not to check the data. You don't care about it. I mean, you have to check and see if the data is roughly linear, the first condition, roughly linear. And then you check your residuals. And I hope I answered your question. I wish we could write more details and explain exactly what the math behind it. And the constant variability. The variability of points around the least square line remains roughly constant. And I will show all that in the graphs. And this is one of the most important element is the independent observations. And one time I was explaining this concept to someone and they asked me, how do you make sure things are independent in real life? And so I gave the example that if you wanted to check to fit a regression between height and weight of people, then the observation should be independent. So what it means is you don't go and take just observation from Kofi family and you take Kofi's mother, Kofi's father, Kofi himself and his brothers and siblings, and then you come and tell me that's the model that explains the general, the height and the weight between people. Because that's a very strong dependent observations. Because Kofi's height depends on his father's height, and you are not bringing any new information. Basically, you only have one single observation if you do something like that. So the question is, how do we make sure in real life, in nature, that it is not dependent? Because this assumption, it is always assumed true, because we do what is known as randomization. So because we take our data randomly out there, even if I measure Kofi's father and Kofi's mother, it is the likelihood of something like that happening is low. And I suppose that whatever is there, there will be something else that I will measure that will cancel this one out. It is known as confounding factors. And the randomization helps you break those confounding factors or confounding errors. So this is something that is important, and you need to understand why we don't really spend the time checking it. But if you have to design a survey yourself, then you need to make sure that you don't just go and measure things from your friends. Like you want to check what is the relationship between people eating koliko or most of you are from Nigeria, so I don't know how to call it.
Fries, it's better.
People eating fried yams and their height, and then you go and measure it in your friends. That will give you the information how your friends like, but that information is not variable or diverse enough. It is basically having one single observation. So you need to go and measure it in different corners and different people to be able to make strong conclusions. Because you can always make a conclusion, they are just weak. To make strong, you need these conditions. And even if your residuals are not normal, you can still make conclusions, but they are not strong. I want you to understand it. So let's come and see some cases. So this is a case where you have the data is not looking linear at all. Like you can see, they look like a curve, like how do you call it? A convex curve, that's what we will call it. How do you call it? Bell curve, right? Yeah. And if you fit a linear model, that will be your linear model, and that's how your residuals will look. And you see these residuals are violating this assumption of constantly variability. I mean, it is the same. It is, the variability should be the same along this, like this, all this is too much. And here you have a model that is quite linear. So you have residuals that look exactly linear and constant around the mean, their mean. And here you see you have this kind of shape that goes up. So basically, do you understand why I said you don't really care about your data? Because residuals will tell you everything you need to know. So you don't really need to care if your data was normal or not. Residuals will tell you if your model is good or not. And this is another case where you have your data is not that linear. It is like cyclic data. And this comes from time series. If someone already analyzes some kind of time series or something like that, it's like a phenomenon that is decreasing, but decreasing slowly. And you can observe it in your residuals. So residuals plots is very important, and you need to pay a lot of attention to it when you fit your models. Let's take an example. So you have here 3 height and 3 dBH. And I don't know if you know what is 3 dBH. So it is called the diameter at basal height. So it is the diameter of the tree. Let's just make it like that. So can we predict the height of trees? And we have a few foresters here. They can tell you how difficult it is to measure the height of a tree. It is easier to just measure the diameter, but the height, it is a lot more complicated. So if you can have a model that predicted the height of trees accurately just using the diameter, you will make a lot of money. Although it is an old problem in forestry, it is a problem that is still investigated, and many companies out there are still paying a lot of money to people just for that. So this question, can we predict? So it is a regression problem. And we can go to our whole process to calculate the R. And then if we fit it, I mean, you don't need to calculate this correlation coefficient, that's 0.5. You don't need to calculate it before fitting it on R. But if you do so, you will have it. And then you can calculate the slope and the things. But you can directly fit it on R. And it tells you that the intercept is 62. And so basically the interpretation here is, I come back. If there is no diameter at all, the height of the tree will be 62 centimeters. Something that may make sense or may not make sense, depending on how you measure your diameter. If you suppose that a diameter is smaller than something is you cannot measure, then this makes sense. But if you can measure diameter up to 1 millimeter, maybe it doesn't make sense. So that's why I say that you need to question your data all the time. And this one, it says that that's the slope of your line. And both of them are significant, the p-value. Another element that you should pay attention to is the p-value. And this is the residual plot. And you see the residual plot is telling you that there is a kind of trend, but that trend isn't very strong. And they tell you that the 0.20 in your data set and the 0.18, 6, maybe they need to be checked because they are very, very far from all others. And so here we don't have it. So if you have the order of your data, you will see that maybe this is 6, this is 18. So something like that. I'm not sure. And to check the normality of the data, you need what is known as QQ plot. I think John covered it last time, right? Anyway, and the QQ plot is saying the same, that the 0.6 and the 0.18 are quite suspicious, including the 0.20, and maybe they need to be checked. If the data was, if the residuals were normal, they would almost follow this line. And this is the model that is fit. So this must be the pointer, the negative one, and this is the positive one, and maybe this one are the ones that they are telling us we should check, double check. So, and finally, we have R square of 0.26. That is our coefficient of determination. So basically what it is saying is just using the diameter, you can predict 26% of the variability in tree height. Is it good? Is it bad? Depends on how important this parameter is. So you have to understand that it is relative. It is really dependent on what you are looking for and how important it is. So, and these coefficients show that they are significant. So your model is statistically highly significant. But now we go to the business side. If you go and tell a forester that, oh, I have a model for you that will predict your tree height now, you don't even need to struggle anymore. You just need to take the diameter and I will give you the height if you give me the diameter. And he will be like, or she will be like, really? And what is the coefficient of determination of that model? You tell them 0.26. They can be like, oh, shit. Sorry, excuse my language. They can be like, this isn't what we want. This is so bad. Maybe they wanted 0.99. So that depends on the business. Or in some business, they will be like, wow, you can explain 26% of variability in our data. That's a really good model. So when you have a result like this, you need to take into account the business aspect and how difficult it is for that business. Mute Alex. Okay, done. So now there are other methods to explore if like this line, is it significant? Is it good enough? Not the R square only. So you can use a test of a hypothesis test and check beta 1 in this case is our B. So is it like our slope? Is it 0 or is it significantly different from 0? Or I think this is not really the matter of my presentation, so I will go to it too quickly. So basically, R is already doing it when they give us the p-value. Basically, they are checking if it is statistically significantly different from 0. And so when you have a p-value that is less than or a bigger p-value, let's say that a p-value of 0.5, that means that your parameter, although it is 62, it is not that different from 0. And when that case arises, your standard error will be high, very high, that the standard error will, maybe in this case we have 62, and let's say that we have a standard error of 60. So it is very likely that your model will not be statistically significant. So now we go to a different topic that is more interesting, is categorical predictors. I mean, everybody and all the time you will see it is about numerical predictors. Like you are trying to predict the height and the weight. Both of them are numbers. What happens when it is not numbers? Maybe you wanted to check the theft rate in Los and or in Benin City, and what you want to use is the category of people. Is it like having more young people, age class, like how young or more adults or more juvenile, explain the number of theft in a city. And in this case, you are not using numbers, it is just age class. So the question area. So let's say you want to predict the growth of a crop under shade and non-shade. So you will have two categorical predictors, like a categorical predictor. So that's a different case than what I presented before. And the idea here is you cannot just use them like that. You need to find a way to change the data. And I will talk about this example more. And this is a tiny bird. People that like birds, they will love it. So they are trying to predict the number of birds. Does it depend on the height, like the elevation? And what is they are using is the elevation class, like high, medium, and low, instead of using just elevation like that. And this is that nice looking bird. And I know maybe in West Africa, we don't care about the birds, but in Western countries, birds are a big deal. So, and they collected the data on 238 locations in Switzerland. And the question is, can we use the elevation to predict where you will have more birds? So that visitors can just go and they know that if I go to this elevation, for example, I will have more birds. Basically, that's the question. So basically what you do here is what is known as dummy variables. You need to change this into dummy variables and then you use it in your model. And when you do something like that, we care about them a lot. I'm one of those that care about them. Okay, Joseph, that's cool. Thank you. Yeah. So we don't talk a lot about them. I should say that we care, but we don't talk a lot about them. Here it is where I live in Washington State. It is a big deal, and you have clubs of bird watchers and people going to watch birds. And I am in a school where there is a whole department that only does avian studies, and they study all kinds of birds, crows, and things like that. So it is a very, very huge deal. And I mean, you can go and kill a lion or whatever they have here. Everybody will be fine. But you shoot a bird, people will have a lot of trouble with you. And you will have to defend yourself. So birds are a big deal here. So I was saying that what you have to do basically in this case is you transform it into dummy variables and then you put them in your model and you get this kind of result. And I didn't have an example on it, but I can create some dummy variables during our practice so you can use it. I think I needed to slow down here because this aspect is not a lot taught in schools, but it is one of the things that you will face when you will start working. Because in real life, not everything is in numbers. And like I said, this elevation, they were actual numbers. You could put the 500 meters, 550 meters, 590 meters, and so on. But it doesn't make any sense. Nobody wants that. So what people want is this kind of classes. And that's what you will have in the real world, like young children, juvenile, adults, and older people. Even if you are working for a bank, the bank will classify people into age classes and then try to see who are the good customers and who are the bad customers. Should we give loans to young ones? Or so it is going to be a lot of categorical data, and you need to know how to use them. And I mean, currently I'm working, and I have seen, I will tell you about it a bit later, models that have more than 100 or 200 predictors, and maybe 75% of them are just categorical predictors. So categorical predictors are more common than numerical predictors, although we don't say it a lot. So what does p-value tell us? This is something that is nowadays a topic or like a contentious topic or something that causes a lot of friction between the scientists. Should we report the p-value or not? Is the p-value really necessary? And this one, I leave it there. And I will just tell you, if you wanted to, you are curious, you can check this one called the Bayesian statistics. So you can check what is known as Bayesian statistics. And it comes from one guy called Bayes. And the idea, what I am explaining here, presenting here, is known as freak statistics, where the p-value matters, where we suppose that we have it, the theory is a fix, and the data, we are trying to fit the data to the theory. And so we need a p-value. But nowadays, some people are very, very strong, and they are like, no, the p-value doesn't matter at all. What I want is, I will fit the theory to my data. So the theory becomes the variable and the data. So the theory has to fit to the data. And in that case, you don't need the p-value. So you have more information when you have more data. I am not going to go in that debate, but I want you to know it. When you see it somewhere and someone tells you that I don't want to report my p-value doesn't matter that much, you have to understand what they are talking of. Now, one other more important aspect when we are working is outliers. I think outliers are even more important than p-value, because if you have outliers, then your model is only good as your data is good. But the question we face all the time is, what is outlier exactly? What is an outlier? Is it the outlier the data set that I don't like? Or it is the data set that I wish I didn't have? And so what we do, we could take a guess, right? And then just remove them. But that is what is known as non-reproducible work. And I think John presented it last time, and he showed that you should have your model and your work set in a way that anyone in the world can reproduce your work, exactly do what you did. And if you just remove outliers, then you will not have it. So the rule of thumb is we can just flag the points and is more than 2 standard deviation and consider them as outliers. So this is more systematic. But to be honest, when I read the paper and they tell me they remove the outlier using such a rule like, or something like this, I'm skeptical about them. And I am like, they must be just saying whatever they want. So the most common method is to have just data that are with outliers and without outliers. And we present both models. And then we let the reader decide how they feel. So let us see how outliers may influence. So this point can be considered like an outlier. And you can see it in the residuals. So underneath is the residuals. Again, this stresses the importance of residuals. But I jump quickly, and here you have the outlier that is high there, and that's it. And this one. So if someone wants to speak, do you think it is an outlier or not? I will call on someone again. Ojoa.
I would like to say something even before Ojoa speaks. You know, Ojoa is also a former Med4 student.
A former Med4 student?
Yeah,
really?
he was in Portugal. Yeah.
Which edition?
1 year after us, we studied together in Portugal. This is my second year.
Really? Okay, Ojoa, welcome them. So it is your time to speak. Let me unmute you.
Hello.
Yeah, Ojoa.
Yes.
How are you?
I'm fine, thank you.
Okay. So, okay.
Sorry?
I think someone is speaking louder than you, so I will mute you back and
Sorry.
ask someone else.
Okay.
Thank you. I'm having a hard time finding people. I don't want to pick on our Asian friends. Okay. Olua Toby, what do you think? I will mute you, unmute you. Olua Toby, are you around? Okay.
Yeah, yeah, sorry, my network fluctuates. Can you come again with the question?
Yeah, so my question was this second graph, the 2. What do you think? Is this point an outlier or not? And remember, before answering, in reality, you don't know before fitting the line. So if you had just the scatter plot, the data, do you think this is an outlier or not?
I think it is.
Why do you say so?
If I'm to use the first explanation from the graph 1,
Yeah.
it discovered that this point is totally far from the rest.
Okay. Thank
so
you
it's
for
like the, okay, thank you.
No, go ahead.
Okay, so the point is totally far from the rest. So it's like you said, it's like the side that you don't want in the rest of the data set.
Okay, thank you.
Yeah.
I think from your explanation, I get one aspect is the point you don't want. Okay.
Yes, sir.
Thank you. Okay, I think Oluwatobi just made a very good comment, and I thank him for his participation. And he said something that I said before, that it is a point you don't want. That's not what an outlier is. In fact, the outlier is the point that the scientist doesn't want. It doesn't mean it is not a true point. So let's take an example that I didn't ask Oluwatobi where he's from. So let's say that you live in a small village in Ghana, and what happens is everyone in that village is quite short, and you measure them, they are quite short and fat or something like that. So they have small height and very high weight. And then you have a skinny guy, one single skinny person who is quite tall and quite lightweight, and their data point is here. Is it an outlier? No, it is not. It is the truth. And you really wanted that data set because that person represents some reality in that village. And if you miss that person, then, oh, okay, there is a problem with data set. So if you have a problem with that data set, if you miss that person, then you will miss some critical information. And this is a case that happens in some of Western countries where they have one single Black person living in their neighborhood. So each time that person will be like an outlier. But this is not an actual outlier. I wanted you to understand it. That outlier doesn't, if you have a point that is suspicious, it doesn't mean it is an outlier. It may just mean that you need to go back and double check your data and to understand why it is there. So in case where you are sure that it is an outlier, it looks very different from others. That's how it will show on the residual plots. That's my point here. My point here isn't to tell you that all these points are outliers. I mean, this one, I can say it is an outlier, but this one, I am not sure. This one, I can say it is an outlier. To highlight something. Outliers can completely, okay, someone gave an example, an answer. So I don't think it is an outlier because it follows the trend. Yeah, it can be the case. But in any case, the whole point is you need to double check this kind of point. You don't just assume that they are outliers and remove them. And like I said, removing may not be the real way of dealing with it. And thank you for your participation. I like to see those things coming because it helps you to see that you are following. The most important graph on this thing, I think, is the graph 5. The graph 5 shows exactly why outliers are a problem. Because in reality, this cloud of points, they are not linear. If we didn't have this point, the line we would fit would be just a horizontal line like this with slope 0. But because we have this point, it is pulling the trend to go up. So if you fit a model like this, then you will be like reporting a very high R square, a very high, you will be reporting a lot of things that don't exist. So that's why, again, I said that the residual plot is one of your best friends, because in residual plots, you will see it clearly that there is a problem, why this one is there. And so this one is really something that you need to double check, why this point is there. And it is very likely it is an outlier. So in a case like this, even if it is not an outlier, you need to report it and spend the time explaining what it is and why it matters to have it. If you cannot support why it matters to have it, you remove it and you analyze it again and you present the result. And so you show that without the data point, the result would be a very flat line, horizontal line. With the data point, you have this trend. And you need to spend a lot of time in your papers and in your research to explain why that point matters or why it doesn't matter. You cannot just remove it and be like, now I am done. Or you cannot just keep it, because this point is very problematic. And in this case, it is not problematic because it goes almost like this. So it is possible that, I don't know, if we take the example of that village, you have someone who is short. So people are born with some disformation. So that is something that can happen. But something like this, you need to spend a lot of time trying to understand it. Good. So we move on. So what do we do if we identify what we call outliers? In general, we do nothing. That's the reality. All the data should be used when calculating statistics. Researchers cannot just use only the data that they like or that fit their hypothesis. And the last point is, in most cases, the best and sometimes safest approach for presenting statistical measurement is with and without outliers being included. And doing so, you let the reader decide how it should go. And I am not going to present it here. Once you go in more advanced statistics, there are methods that are robust to outliers. And some of those models, I will write them here and leave them just for you. And you can hear what is known as region regression and lasso regression. So why I am not presenting them here? Because to present these models, we will need more than 2 hours or 3 hours, because you need to go in the background and explain what is an optimization model and explain what is known as OLS, ordinary least square, where you are trying to minimize the residuals. And then before being able to present these models that are known as constrained models or regularization parameters, because they have something that is like pulling the outliers, or one single point weight isn't going to be as strong as. So if you have such, like if we have like lasso or region regression, this thing would just be a flat line, because this single point, its weight is not that important to pull the line up. But this is beyond the scope of this teaching, so I leave it for now. And if we get the opportunity in the future, we can present more advanced material like that. And those who are interested, I just leave the name so you can read them. And sure.
Someone has a question.
Okay.
You switch. Ojo.
Yeah, what's the question?
Ojoa, if you're listening, you can.
Yes,
speak.
can you hear me?
Yes.
Okay, so in last slide you said that it is unethical to remove outliers just to improve the model.
Yeah.
Right?
Yes.
In case where you are contracted to do some kind of studies to, for example, you are a forester, I would say. I mean, so for example, mountain farming, for example, and then you are contracted to do some studies and give some recommendations to make some policies, okay? And then, won't you be left as the researcher you'll be left with the option to either remove the outliers or not, because those you will be presenting your results to, maybe the policymakers, the local government, or something. They might not really understand, okay, the difference between the results you get with the outliers and the results you get without the outliers. So how do we justify this?
Yeah, that's a good point. A good point is of a scientist is, at least in this context, I will say a data scientist is to be able to take a very complex problem and then translate it into data problem, solve it with the data, and then translate it back to actionable decisions. And like you said, the policymaker doesn't care about your point and the outliers or without outliers. But there is one person that you will be working with, who is the person who collected the data and what those outliers represent, because you will have to spend some time to understand them. And like I said, if outliers are a tall person or a group of minority group in a village that are taller than the rest of everyone else, they are not outliers, they are still there. So you can make policy that is clear that if we wanted to impact one, you wouldn't outliers, because you are not the policy maker, right? So if we want to impact everybody in this village, this is the actions we want to take. But there is a trade-off. If we want to make maybe a cheaper action that will impact and negatively affect a group of people, this is the different set of action. Like you said, you are not the policy maker. So it's this one, you are not showing them the outliers, but you are just telling them different actions they will take and what is the consequence of each one of them. And that's what the outliers are. And maybe I went a bit faster and I didn't say something. There's something that can be considered outlier that you are allowed to remove. So let's say that, I hope I answered to your question. And I go ahead and talk. Let's say that you are given a data set and they were entering maybe the height of people or something like that. They were entering some salary of people. And then there are some people that they couldn't know the salary. And since they couldn't know, they just enter 9999. So, or 3 nines or 4 nines or something like that. So it is possible that you remove something like that. You don't even have to worry about that. It is an outlier and it is clear that the salary couldn't be 9999. Or another case is the age of people. So people are coming and they are doing a census, and then by mistake, the typewriter wrote that the age of someone is 200. So you know that the ages can't be 200. So it is either 20 and the person made a mistake and wrote an extra 0, or you don't know. So that is an outlier. You can remove it and get rid of that one. So that's the only case where I advocate for removing outliers. Everything else is analyzed with and without, and then make a recommendation with and with as well. And it is very likely and sometimes that you will end up with the same recommendation with and without outliers. I hope I answered to your question.
He said yes.
Yes, understood.
Thank you. So the other thing that I will do to conclude this section about linear regression is extrapolation. We love it, don't we? So let's take this good example. Yesterday, this woman had 0 friends, and today she got married. She has 1. So we can already fit a line, right? And so if we want to say how many husbands she will have tomorrow, that will be already 3. So as you see, by the later next month, you will have over 4 dozen husbands. So that's the extrapolation. You take a set of data and then you project that it will be the same in the future. And all of us do it. It is not only this, but I want you to make a distinction here. Extrapolation is a little bit different from prediction. So if you want to predict what the person will do in the future, that's a bit like extrapolating, but the idea is a little bit different. It is not a regression, because a regression is interested in taking the coefficients and making some interpretation based on those coefficients. And that's what this person did. So I want you to understand it, because we do it. Maybe you will build a model that works very well in Ghana, and then you take it to Nepal. And you are like, yeah, this model worked very well in Ghana. Why it won't work in Nepal? It may not work. It may work perfectly as well if conditions are the same. But if you are just extrapolating and you are like, since it works here, it will work everywhere. No, that's not how it works. Maybe you will have to build it from scratch when you go there. But you need to understand that idea of extrapolation. That is like doing prediction beyond what your data covered. Like if you measure the height and the weight relationship in Ghana, it's not going to be valid if you go to Tanzania. Those people are tall and skinny, so your model wouldn't do anything at all there. That's the idea of extrapolation, and it is a dangerous idea. Okay, I can move now. So now we go to multiple regression. That is much easier, and if you understood the linear regression, you just needed to add more variable, more predictors, and then you get the multiple regression. Very simple. There's nothing to add. So it is the same. We had this before, up to this point, X1, B1. Now you add more predictors. And this is not in the scope of this teaching, but multiple regressions come with a lot of constraints. I will leave it for now. If we have time and opportunity to have like a follow-up, like a higher level of this training, I can cover more aspect of it. And so the idea here is you have only one dependent variable, and each independent variable has a fitted slope. So you will have slope for each one of them, and only one intercept. And we go back to our data set. We will have width, length, petal, sepal. So you can just use one of them, like the sepal or the sepal width or length, and try to predict, use all others to predict one. So that's a multiple regression. So the petal width can be predicted by an interceptor plus B1. And okay, before I go, some of you are interested in what is known in data science. And what this intercept is called in data science is what is known as bias. I will write the word bias. And why it is called the bias there is something that I can quickly say that it means that it is the average, basically. It means that if everything else is 0, 0, that's what you will get. So it is like the model, your model bias is a bias by giving you always this value. So that's what is known as intercept. And in the world of data science, it is known as bias. So I think I am taking you from simple models and trying to excite you, to motivate you to read more about more complicated modeling. So if you have something like this, then you have a multiple regression. And in R, it will be the same. You will have your intercept that will still be there. And then you will have each of these parameters predict, and then you have the p-value associated to it. In this case, it means that the intercept is strong, highly significant, followed by the petal, not followed. The petal is highly significant as well, and this one is just as significant, the sepal width. To predict, I don't remember what we were predicting, the petal width. And I think John presented this one last time. So archaic index of C stands for what, Doji? Archaic index of correction or something like
archaic
that.
Information criterion, you mean, AIC?
Yeah.
Archaic information criterion.
And this is beyond the scope of this thing as well. But multiple regression, you cannot just use R square. You will have to use other kind of parameters like adjusted R-square or BIC or AIC. And to understand them, then we need to go to more advanced materials to understand them. But it is good to just have an idea that there's a parameter that exists called like that. So I said before that R-square yeah, I said here that R-square is just the square of the same as taking the square of the correlation coefficient R-square. That's the, and I said that it is only valid for linear regression. In the case of regression, completely different. And this is a point that I want to make. In this case, you have what is known as a R-square. You have it is 1 minus R. R, that is the correlation coefficient, and N is the number of observations, and K is the number of predictors. So this adjusted R square can be negative. I want you to understand it. This one can be negative. The other one couldn't be negative, but this one will be negative. So this one isn't between 0 and 1. This one is, the maximum it can take is 1, but the minimum it can take is negative something. And I want you to understand it because I saw many people debating if R square can be negative or not. And they are like, no, it is the square of the coefficient, correlation coefficient. It is true in the case of linear regression. But when you go to multiple regression, you will can get it negative. And someone will be asking, how on earth can you get it negative? So let's suppose that your correlation coefficient is 0. So this term will be 0, this one. So this one will just be 1. So you will have n minus 1 divided by n minus k minus 1. And let's say that k is equal to 2. So you will have n minus 3. N minus 1 divided by n minus 3 is greater than 1. So you will have 1 minus something that is greater than 1. So you will have minus something. I don't know if you see it.
Yes.
Perfect. So don't put in your head that R square, adjusted R square at least has to be always positive. No. And in the case of Irish dataset, I will just give you directly the adjusted R square. Not in this case, but R square adjusted, you can calculate it yourself, like in this case. And the coefficient of determination is 0.8, sorry. And these are just examples. You will have this thing to read through. So there is another aspect that comes. Let's say that, and I think we will take a break after this so that we can come back and finish with the practice. So let's say that you have a model of this kind. And the question is, I have many predictors. Like I want to predict the salary of someone. And I have their weight, their height, their level of education, their background, how many children they have, and many other information about the people. Does it mean I need to include everything? Does it mean that the salary of someone depends on their height or on their weight? Maybe, maybe not. I don't know. But the only way to know is to test it. So if you fit all those things in the model, then you will have an adjusted R square. Like you can see in the adjusted R square formula, we have K here. So more elements you put, more this thing will be smaller, and you will tend to have this this relationship being tending to be greater than 1, or tending to get closer to 1. So your adjusted R square goes lower as you have more of K's that are unnecessary. So you need to have what is known as a model selection to only select the parameters that make sense. one way of doing it is to fit a linear regression, like just one element at the time, and then see the ones that give you strong linear regression, and then only use them to build a multiple regression model. I pause there and I will repeat myself again. One way, and it is not the only way, one way to do it is to build simple linear regression between your response variable and each one of the predictors. So in the case of salary, you build a linear regression between the salary and the weight of the person, people, and the salary and the height of people. And so each time you will get an R square. And then you decide on which model, which predictor makes sense based on R squares. And then you select only the ones that give you stronger R squares to build your multiple regression. It is not perfect. It is not the only way to do it, but that's one way of doing it so that you don't have a bunch of predictors that are unnecessary. And finally, and the thought on regression. There is a lot of literature on regressions. And regression, since I started working for Amazon, I have seen regressions that are beyond what I thought is possible, at least beyond what they taught me in school that regression should be used for. And they use it in production, in real life, and they make a lot of billions of dollars using such models. So regressions are not that unimportant or are not that very basic models. And what they use isn't more complicated than what I showed here. It is more predictors and more stuff, but it is the core principle is still the same linear regression or the same multiple regression. And if you understand how to do multiple regression, you will understand it. It is the same concept every day and all the time. And so understanding the core and the core principle of it is very important. And be aware of making extrapolation, that's a prediction beyond the data. All the methods in this part of the course are based on assumption of linear relationship among variables and the assumptions of normality. That's what they tell you, but I will tell you it is normality of residuals. This will not always be the case, and there are other types of regressions and ways of nonlinear relationship, and Kofi will present all that. And logistic regression and spline and all other kind of regressions that are not linear, like moving averages. And those are taking us a little bit more away from statistics, and we start going into data science and other stuff. And finally, I think I will just say one word about ANOVA. And ANOVA itself is a linear model. It's not linear regression, but it is a linear model where you are just using the mean of observations, but it is still the same model. If you want to write it mathematically, it is the same like what we wrote. Y is equal to A mu 0, that is like the bias, plus X. I am speaking by myself. I know nobody is following what I'm saying, so I leave it there. But this mathematical formula, where is it? This mathematical formula, the way it is written like this, I will have to remove these letters and put like mu, and you will get it is ANOVA. So it is the same mathematical concept behind. And that's it. I stop here and thank you for your attention. I think the moderator, we take a break of 15 minutes or how long?
Okay, thank you so very much, Mr. Martin. Hello, can everybody hear me?
Yes.
Yes.
Okay, I'm sure you would agree with me that Mr. Martin have done much, in fact, more than what I even expected. Please, can we say some words of thank you? Thank you, Mr. Martin. And
we are not done, right?
Yes, I know, I know. For this first section, you know, we're still coming back for the practical section where we'll learn how to do some of these things using the R. But at first, let me say thank you. And this short break will be going on. I would want us, you know, we've been seated for a long time. You can stretch your body and you can use the convenience and we'll reconvene again in the next 15 minutes. Like I said, this is 11:40. Okay, let's meet 12 o'clock. That's in the next 20 minutes.
Okay, sounds good to me.
Yes, so at exactly 12 on dot, we'll reconvene again. But this group, I won't close this platform, so we can interact with each other. We can talk. We can get to know each other very well. And when it is 12 o'clock, we'll be back again. Thank you.
Okay, I will be online, and if you have questions, I will be here to answer them.
Oh, good.
And I want to ask someone, Anjana,